Okay, so thank you. So the notes that I've written up, I've outlined sort of two flavors of results. So one I talked about in the first half, which is about sort of non-existence of results or finiteness of results. The second sort of results are about when there are actually actions. So it's a story about actions on the torus, where there are some actions and you want to classify them. And so I hope to say something about that at the end. But I want to start by continuing with the story from the first half. And I actually want to, you saw the higher rank assumption in the statement of the theorems, but you didn't actually see it used. You didn't actually see that there's this higher dimensional group of diagonal matrices at all. So let me try to explain to you how that appears. So this one should come up first. So here's a construction that we use, and it's certainly not an original construction, but somehow our use of it is somewhat original. So this is called the induced action. And in my notes, this was bullet point 5. So it's called the induced action. So again, G is S, L, and R. And N is always at least 3, so this is higher rank. Gamma is some lattice subgroup of G. I have a manifold, and I have an action of gamma by some sort of diffeomorphisms of M. And so from this, I actually want to build a G action on some auxiliary manifold. So let me just outline that construction for you. So you start with G times M, and this will be some covering space for the auxiliary object. I'll have gamma act on the right. I'll have G act on the left, and I'll tell you what these two actions are. So if you take the order pair Gx, and you hit it on the right by gamma, you want this to be G hit gamma. And then to make it a right action, you want to take alpha of gamma inverse of x. So that's the right action. And then there's a left action, which is G prime hit G comma x. This is just G prime G comma x. So this G action looks like it does nothing in the second coordinate, but then we're about to quotient by the right gamma action, and so then, of course, the two things get intertwined. So you can take G times M, and you can quotient by this right gamma action. And then you can check that these two actions commute, and so then there's an induced G action on this object. And so this is where all the games are played, are on this object. So we let M alpha be this quotient. And this has a structure of a fiber bundle. So M alpha is a fiber bundle. Because you could just ignore the second coordinate. So it's a fiber bundle over G mod gamma. And the fiber is diffeomorphic to M. If you know what a mapping torus is, for where you just have a single map of a space, you do the same construction. So instead of a mapping torus here, we're getting a mapping G mod gamma. And there's a G action on this fiber bundle M alpha. And this G action commutes with a projection to G mod gamma. And so there's a G action on G mod gamma on the left. And it's really this object that we want to study, this induced G action on this fiber bundle, projecting over the G action on G mod gamma. All of the nonlinear dynamics of alpha on M are encoded in what happens in the fibers of this action. And then downstairs, we have beautiful homogeneous dynamics where we know, well, I want to say we know everything, although lots of people had to work to figure out properties of this action down here. But somehow we're able to couple the nonlinear dynamics up here and couple that with some of the homogeneous dynamics down here. And so in particular, I have my favorite subgroup, A inside of GL, inside of SL and R, which is the group of positive diagonal matrices. So I think of this as Rn minus 1. And a lot of the work is, instead of looking at the G action up here, we look at the A action on this M alpha projecting over G mod gamma. And of course, the A action on this. And so, of course, there's a lot of work about the A action down here, a lot of things known, and then somehow we can say something about what's happening in the fibers by studying the A action on this total space here. So I'll give you a flavor of some of the things that we can do with this construction. So I'll tell you the measurable rigidity. And I'll tell you two stories here. So one's the easy story, and I'll try to tell you the fancier story as well. So here's a proposition, which is the following. So I have A acting on this fiber bundle, and it projects to A acting down here. So let's let mu be an A invariant probability measure on this fiber bundle. So A is an abelian group. So you have an abelian group acting on a space. We can let's take this to be, let's assume that gamma is co-compact. So this is a compact manifold. You have a continuous action of an abelian group. There always exist invariant measures for that action. But there's no reason for there to be a G action. There's a G action, a G invariant measure. And I want to assume one property of this such that, well, I can look at its image, it's marginal under this projection, and I have a favorite measure on G mod gamma. My favorite measure here is the one induced by the Haar measure, so I'll just call that Haar. So such that this projects to the Haar measure under the projection from M alpha to G mod gamma. Okay, so such a mu exists. We can find one that projects to the Haar measure, and this exists. So if the dimension of M is strictly smaller than the rank of G, which of course is n minus 1, then, and let me just be careful. So I said diffeomorphisms, and so let me write diff2. You can show, and this actually isn't that hard, that then mu is automatically G invariant. So again, there's no reason for there to even, just from abstract nonsense, for there to even exist a G invariant measure on this object, on this M alpha, because G is not an amenable group. So just because you have a continuous action on some compact metric space, there's no reason for there to be an invariant measure. When the dimension of the fibers is sufficiently small, this is a relatively elementary proof to show that this measure has to be G invariant. And this is a key step in the proof of our main result that shows that all these actions have to be finite under a dimension bound, if the dimension of the fiber is sufficiently small. I want to tell you a different story which gives a proof of this, but here this inequality is somehow, this is optimal in the case G is SL and R, but it's the wrong inequality in the case of G is like the symplectic matrices or other R-split groups. So I'll tell you the story that we use for the other groups, even though we end up getting the same dimension count for SL and R. So to tell you this story, I need to introduce a few things. So again, not in the shadow. G is SL and R. A is my group of diagonal matrices, and so again, I write this as diagonal matrices with positive entries. And I have some objects which I think of as linear functionals on A, which I'll call beta ij. These are linear functionals from A to R. And what are they? Well, beta ij of a diagonal matrix with positive entries is Ti minus Tj. So if you know any Lie algebras, these are somehow the roots or the exponentials of the roots of the Lie algebra of G. And I'll be sloppy about whether I'm in the Lie algebra in the group and whether I'm taking exponentials or logs. So here's some linear functionals on A, and they come from the structure theory. And associated to each of these is a one-parameter unipotent group, Uij. This is the one-parameter group. One parameter root group. And so just rather than telling you a definition, let me just write down an example. So maybe U2, 3 inside of SL3R. It's the matrices of the form 1, 1, 1, 0, 0, 2, 3. So it's a one-parameter unipotent group of this form where you're 0, your identity, you're 0 everywhere except in the corresponding entry here. OK, so here's some just algebraic data associated with G and somehow associated with the A inside of G. And there's another set of data that's dynamical as opposed to algebraic. So now let's let mu be an A invariant. And I will, just to be technically correct, I'll say the word ergodic. This just means that it can't be decomposed into other A invariant measures. So it's one that's indecomposable. An A invariant probability on M alpha. So again, in M alpha, I can look at what happens in the fibers. And I can look at the dynamics in the fibers. And similar to how we have algebraically defined linear functionals on A, we have some dynamically defined linear functionals. So there exist linear functionals which I'll call lambda I superscript f from A to R. And these are called the fiber-wise Lyapunov exponents. And rather than giving you a formal definition, let me tell you some of their properties. And I left a big blank space there, but I think I'll still come over here. So what are these linear functionals measuring? Well, if I stand inside of M alpha, then I stand at a point. Well, I have G mod gamma down in the base, and I have my fiber here, which looks like M. And I can look at vectors tangent to M, tangent to the fiber. And I can ask, well, if I take A and A, and I translate this base point, and I correspondingly translate the vectors, I can ask, do they grow or do they contract? And I can ask at what exponential rate. And so if this is x, maybe over here is a n hit x. And some of the vectors have expanded. Some of the vectors have contracted. And so lambda I f of A, this collection, is the exponential growth rate of vectors tangent to the fibers And of course, it's for the dynamics of A. So for some element in the acting group A, you look at what it does to vectors, you get a collection of numbers, and these collection of numbers actually assemble into some linear functionals on the acting group, just using that this is an abelian group. So you get these two collections of linear functionals. You have one coming from algebra, coming from the roots of the Lie algebra, and you have another collection of linear functionals coming from the dynamics of what's happening in the fibers, either that measure the exponential growth rate of vectors tangent to the fibers. And so here's the fancier version of proposition 1. So I'll just call this proposition 1 prime. And it implies the same consequence here for SLNR, but for other groups, this actually gives us much better dimension bounds. So we have these two collections of linear functionals with the same domain, same codomain, so we can compare them. So if we take a root, if beta ij is not positively proportional to any of the dynamically defined linear functionals, then mu, I forgot our hypothesis, so suppose that mu projects to the Haar measure. Mu, I left out some hypotheses. Suppose mu is A invariant on M alpha, and mu projects to the Haar measure. So it's the same initial hypotheses as proposition 1. So if you take a root, which is a linear functional on A, that's not positively proportional to any of the dynamically defined fiber-wise linear functionals, then mu is automatically invariant under the corresponding group, which I wrote with a superscript for some reason. So sort of the philosophy behind this is that coming from algebra, you have linear functionals, just coming from the structure theory of semi-simple Lie groups. Coming from the dynamics, you also have some linear functionals which say something about what's happening to the nonlinear dynamics in the fiber. And this is the philosophy behind this proposition pops up in a lot of our work, which is that if the algebraically defined linear functionals are not positively proportional to the dynamically defined linear functionals, then you get some extra invariance of your object. All we assumed was that it was A invariant. Here we get that it's invariant under a lot of these unipotent groups. If the dimension of the fiber is really small, there's not very many of these objects, whereas there's a lot of these guys. And so then we could get invariance under a lot of these unipotents, and then we get invariance under the full group, which is how you can prove proposition 1. So with either of these two propositions in mind, I want to just outline the proof of our theorem B. And so, of course, let me remind you what that was. So I don't know what it is, but I know that 1 is less than I is, so I know that, I don't know that I can go all the way up to dimension of M, but I know that so it depends on whether I count them with multiplicity or not. So if I count them with multiplicity, it's at most the dimension, of M, yeah. But there's at most the dimension of M of these objects, yeah. So now let me remind you, proof sketch of our theorem B, which is this result in dynamical systems where the geometry is supposed to control the the growth of the derivatives. So we have an action by diffeomorphisms of M. And the dimension of M, I'll just do the non-volume preserving case, so I'll assume that this is at most n minus 2. And then I want to show that if I take the derivative of the corresponding element gamma, if I take the norm of this, that this is at most c e to the epsilon, the word length of gamma. And of course, there's quantifiers, so for all epsilon, there should exist a c where this is true. And the proof boils down to, in all three of the papers, boils down to establishing the following key proposition. Which is the following. So if the thing we're trying to show is false, then there is an A invariant probability measure mu on M alpha such that, so there's an A invariant measure on the suspension space such that 1, mu projects to the Haar measure under the projection from M alpha to G mod gamma, and 2, we have this collection of linear functionals which describe what happens exponentially to vectors in the fiber. And I can assume that one of these functions is not 0 for some A in A. So these are linear functionals. Of course, they could be the 0 function as linear, but I'm going to assume that at least one of these is non-zero. And so the key proposition is that if the thing we're trying to prove is false, that we can build this measure. And from this, we get the proof of theorem B. So this is the first bullet point, is the key proposition. Second bullet point is that using either proposition 1 prime or proposition 1, we have that mu is G invariant. And then finally, there's a contradiction. So again, we're assuming that the dimension of M is small. So then we have a contradiction. Zimmer co-cycle superrigidity will give us that there's a G invariant. Again, it's only measurable, but that's OK. Measurable Riemannian metric. Well, of course, there's not a G invariant Riemannian metric on all of M alpha because G really distorts in the base, in the G mod gamma direction. But there's a G invariant Riemannian metric in the fibers of M alpha. So because we have an invariant measure, a G invariant measure, because the fibers have low dimension, Zimmer will tell us that there's a measurable invariant metric. So we're acting by measurable isometries in the fibers. And so this is going to say that, well, vectors tangent to the fibers, they have to recur to sets where they're bounded. And so this contradicts that lambda I f of A is, let's say, positive for some A. Because this is saying that, well, there's some vector that there's vectors tangent to mu generic points, such that if we apply A, they grow exponentially, whereas this is saying they have to recur to sets where they're bounded, and you can't be recurring to being bounded and going to infinity exponentially fast, so there's a contradiction. So everything reduces to showing this key proposition, which is the main work of all three papers. And in the background, this philosophy that if the linear object, the algebraically defined linear functionals are not positively proportional to a dynamically defined object, that you have some extra invariance, which is how we're promoting something that's just A invariant to being G invariant. So now I forget when I'm supposed to stop. When do I stop? Until 10:55, OK. So now I want to shift directions and talk about I want to talk about some actions that do exist, as opposed to showing that no actions exist. So what I'd like to consider is actions on the torus. So actions on tori. So a little bit of background. So I'm going to take a homeomorphism of a torus to itself. And I'll take a lift to its universal cover. So this is any lift. Any lift is of the form f tilde of x is some matrix hit x plus phi of x. And here a, f, this is in G, L, D, Z. And phi is Z, D, periodic. OK, so any lift is of that form. Just some terminology. I'm going to call this matrix. This is a uniquely defined matrix. You can think of this as the action on homology when you choose a basis. We'll call A, F, the linear data of the homeomorphism F. I'll say that A, F is hyperbolic. If all eigenvalues satisfy that the modulus of the eigenvalue is different from 1. So a matrix is hyperbolic if no eigenvalue lands on the unit circle. And so AF, this induces something which I'll call L sub AF, which is a linear map of the torus to itself. And what is this? Well, this guy has determinant plus or minus 1 and integer entries. So L AF of x plus ZD is just AFX plus ZD. So because this has integer entries and determinant plus or minus 1, there's an induced action on the torus. And there's a nice theorem of John Frank's, which is essentially his thesis. It's a little bit more general than what I'll write, but so it's the following. So if I take a homeomorphism of the torus to itself, and I assume that its linear data is hyperbolic, then I more or less know exactly what this homeomorphism is up to a continuous change of coordinates that might have to collapse some part of the space. So then there is a continuous surjective map H from the torus to itself such that if you apply F and then post-compose with H, that's the same as first precomposing with H and then applying this linear map. So any homeomorphism whose induced action on homology is hyperbolic up to maybe a non-injective continuous change of coordinates, this map is, the abstract homeomorphism is given just by this linear action. And yes, if you want to be very fancy, H is homotopic to the identity. Yeah. I guess it better by this. And that's, of course, how you get it to be surjective. OK, so let's play a similar game. Now let's take gamma, say a discrete group, and let's take an action of gamma, say by homeomorphisms of the torus. Well, you can check that this induces a representation of gamma by GL dz just by associating to every element gamma the corresponding matrix corresponding to the corresponding homeomorphism. So I'll stop writing A sub alpha of gamma, and I'll just call that rho gamma. And you can check that this is a representation. And then, of course, this induces, maybe I'll call it rho hat, is an action of gamma by automorphisms of the torus. Just because these guys have integer entries, so you can do the exact same construction and get an action by automorphisms of the torus. And the question is, again, does there exist an H from the torus to itself as above that intertwines the abstract action alpha with, well, to be the right answer is not quite that it intertwines alpha with rho hat, but that it intertwines alpha with an affine action with linear part rho hat. So there might be some translations in the group just because this might be an action of a group bigger than Z. So you might have to have some translations inside. But essentially, you want to ask, can you find some change of coordinates that takes your abstract action and makes it something that's linear or something that's affine? And the linear part of the affine should be the obvious thing. And of course, the answer is no. If you look at things like the free group on two generators, or its cousin, things like SL2Z. You can definitely find very nice actions of SL2Z that can't be semi-conjugated by continuous surjective change of coordinates to something affine. And again, the reason why you can't do that is that there's just too much flexibility. There's not enough relations in the group, and so somehow you can build actions of the generators that can't be simultaneously brought into an affine form. OK, so here's a theorem. So this one is published. This is due to me, Federico Rodriguez Hertz. And Jiren Wang. And it says, well, you can't do this for things like the free group on two generators or SL2Z, but okay, up to one technical hypothesis, you can do this when gamma is a higher rank lattice. And so again, I'll formulate it for SLNR for n at least 3, and gamma, a lattice subgroup of SLNR, and alpha, an action by, for now, just homeomorphisms of some torus. And of course, we can, if you know anything about this, you can also put a nil manifold here. For n greater than 3, a lattice subgroup and an action by homeomorphisms, and such that, well, what we want is an analog of Frank's theorem. So let's put a hypothesis like that. So let's assume that the linear data is hyperbolic for some gamma naught in gamma. And of course, here, I just mean the corresponding linear action here. And 2, there's a mild hypothesis, which probably always holds. You can check that it holds in a lot of cases, is that this action alpha lifts to an action on the universal cover. RD, I guess. So you can lift individual elements of the action, and the question is, can you lift them in a way that's coherent? And you can do this a lot of cases. It's a question of vanishing of some cohomology. And we need this hypothesis, but it probably always holds. OK, so under these, then, there exists some h from TD to TD, which is continuous, surjective, and of course, homotopic to the identity, such that, and if we assume that this actually lifts when restricted to the group gamma, such that if I take H, post-compose after doing alpha gamma, this is the same thing as doing rho hat of gamma pre-composed with H for all gamma in gamma. And so for the action of this bigger group, or of these higher rank lattices, once we have hyperbolic action on homology, and assuming this mild lifting condition, then up to a continuous change of coordinates, continuous surjective change of coordinates, the nonlinear action becomes this linear action. And the remark, which I said out loud, is that 2 holds on a finite index subgroup, which means, well, if you can lift on a finite index subgroup, you get this on a finite index subgroup, which then means that maybe you're not conjugate to the actual group, to the actual thing of automorphisms, but just something affine. So it holds on a finite index subgroup if, for instance, gamma is co-compact. So this is known, and in general, it's some vanishing of H2 with coefficients in rho. Some vanishing of cohomology. So the defect of being able to lift is some element here. So if you know this vanishes, then the lifting automatically holds. And there's a follow-up theorem, which I'll write, but I won't define the main term. So moreover, if now instead of being an action by homeomorphisms, I'm an action by, say, C infinity diffeomorphisms, and if one of these elements is what's called a Nossoff. So this is a condition on diffeomorphisms, which more or less says that the infinitesimal dynamics sees exponential expansion and contraction uniformly. Then the H that we get above is a C infinity diffeomorphism. And there's some questions about what can you do in between. So if you have a smooth action and maybe you're not a Nossoff, what sort of properties can this H have? But I don't have answers to those intermediate questions. So here's a theorem which, as opposed to saying no actions exist, says, well, we know there are some actions. There are the affine actions that we built from before. Given any lattice and any representation of this form, you can always build an action on the torus. And here we're able to classify them, at least the ones that have this mild hypothesis that you have hyperbolic linear data. So I'd like to sort of sketch the proof of this. And again, I've forgotten when I'm supposed to stop. So is it 55? 55, OK. So I will take however many minutes, 8 minutes to sketch the proof of this. And we saw before sort of measurable rigidity, and this is some sort of cohomological rigidity. So what I'm going to do is I'm going to, again, I have my M alpha, which is G cross the torus, where I quotient by gamma. Of course, here I'm using my action alpha. And now this is maybe not a smooth manifold, but it's a topological manifold, because I just have an action by homeomorphisms. And I also have my M rho, which is given by my action by affine actions, or by automorphisms, which is G cross TD mod gamma, and here it's the action induced by rho. And rather than finding this H, I'm going to find a different H. So the goal is to find H from M alpha to M rho such that, well, one, I'd like H to be continuous, and I'd like it to be homotopic to the identity in the fibers. 2, well, I want H to factor over the identity. So if I have here M alpha to M rho, and here's my H, well, these guys both factor over G mod gamma. And I'd like my H to factor over the identity. And then, of course, I want 3, is I want H to intertwine the corresponding actions on these two suspension spaces. And so I can do H of G hit X, and I'd like that to be G hit H of X. And of course, the hit depends on where I'm acting. So this is, of course, the group action in M alpha, and this is, of course, the one in M rho. But if I can build an H with these properties, a big H, then I have my little h up there. And so you can sort of make a guess for what this H should be. And of course, your guess is wrong. But your guess for what this H could be is it could be maybe you take the identity here and you just lift it to the identity up here. Of course, you don't even know that these guys are homeomorphic. So you take a measurable approximation for this object. But you can make some sort of guess for what kind of H should be. And of course, it doesn't work. And so there's something that measures the defect of your initial guess. And that turns out to be some sort of twisted cocycle. So let me write something down. So this induces, so an initial guess for an H reduces a rho twisted defect cocycle. And so I forgot to write some assumptions that I'm assuming here. So I'm going to assume that my rho from gamma to GL dz, this extends. So I'm going to assume that I have the nicest version of Margulis superrigidity. It extends to a representation of the ambient group. This is a mild hypothesis. So a priori, I only know what rho is at gammas. I'm going to assume I know what rho is at g's. And up to some algebra, you can always assume that you're in this situation. So there's some object that measures the defect of a guess satisfying H, capital H over there. So what is this kind of object? It's a C from G cross M alpha to RD. So this is the kind of object that I want. And then what does it mean to be a rho-twisted cocycle? It means that C of G1, G2, comma X is, and it should be some sort of twisted chain rule. If I do rho of G1, C of G2, comma X, plus C of G1, comma G2 hit X. And in the notes I've explained, written down a definition for this thing. And the key proposition is that the H exists if and only if this defect functional that you build from an initial guess is a coboundary. So what does it mean to be a coboundary here? It means that there exists some function from M alpha to RD such that C of G comma X is equal to rho G eta X minus eta G hit X. Okay, so we make an initial guess for what our H is, and that initial guess probably doesn't work. And the defect of how it works is measured by some cocycle, some rho-twisted cocycle. We want to show that that's a coboundary. And so there's an easy step, which is essentially the proof of Frank's theorem, modulo some algebra, some technical nonsense, which is that you can build a function from M alpha to RD such that, and there's an assumption here which I forgot to write down. So if I take some A in my diagonal group, big A, such that rho of A is a hyperbolic matrix, so for elements, for R diagonalizable elements, such that rho of A is hyperbolic, it's easy to find one function such that you can solve this equation for that element, such that C of A comma X is rho A C of X, eta of X minus eta A hit X. So you can solve this equation, but just for this one element of the acting group. Of course, we want to solve it for every element of the acting group. A little bit harder, but not so much harder, is maybe I'll go to another board. And let me call this star here. If, again, A is in A is such that rho of A is hyperbolic, And if you have a function, which is the potential for our cocycle, or our potential, this satisfies star, then, well, so this function, solved our cocycle equation, but just for one element of the action. It actually is going to solve it for the centralizer. Then eta, then whatever our cocycle is, evaluated at gx, is rho g eta of x minus eta g hit x. And this is for all g in the centralizer and SL and R of A. OK, so we're able to solve the cocycle equation on a bigger group, which is the centralizer of some R-diagonalizable element. But this is still not all of G. Centralizers are pretty small. So what's the idea to actually solve this on the whole group is, can I take 2 more minutes? OK, so what's the idea to solve this on the whole group is that if beta is a root such that, for some A in A, beta of A is 0, which implies that, which I'll leave blank, and rho of A is hyperbolic. Then for U in the corresponding root group, what does it mean for beta of A to be 0? It means that UA is equal to AU. It means that they commute. So I'll just say that this equation, I'll write it again, C of UX is equal to rho of U eta of x minus eta of U hit x. So if we can find enough roots that commute with our diagonalizable elements and such that the representation is still hyperbolic at that element, then we're able to, then whatever solution we had will automatically work on the unipotent elements. And so the goal, let me call this star star. And so then there's a proposition which we prove, which says that if rho is a representation of G to GL dr is such that rho of A is hyperbolic for some A in A, then G is generated by these functions, these root groups U beta for beta satisfying star star. And so I'll stop writing, but I'll just say out loud, what does star star really mean? Well, associated to rho, there are weights of a representation, which are linear functionals on A. B is a linear functional called the roots. And so we have these linear functionals coming from the structure theory. We have linear functionals of rho, which are the weights of the representation. And so what does our proposition really say? It says that we can find lots of roots beta that are not proportional to weights of the representation. And so then we can show that a solution that we get just from Franks' theorem actually solves the cocycle equation on lots of unipotent elements. And then there's enough unipotent directions to build the entire group G. And so then we solve the cocycle equation for the entire group G. So again, it's a non-positive proportionality of linear functionals, gives us extra invariance or gives us some extra rigidity. So thank you. My manifolds are always compact, yeah. We have enough trouble with the non-compactness in the gamma direction, so. I won't answer that question. Yeah, I don't know. So for me, they're always compact.
A question about the affine part of rho hat.
Okay.
Is it some kind of rotation?
It's some sort of one cocycle that. Yes.
So for instance, there's a fixed point at the origin of linear action, so there's some chunk that's invariant about it.
Yes.
But in your case, you said, I mean, if I gave you the nonlinear action, you'd be able to tell me the affine.
If you have like if your group is like SLNZ, then the rotational part, the affine part, is just given by some one cocycle, by some one twisted one cocycle, and so these things exist. I'm not sure how you would actually like probe in and figure out what it is, but maybe you can. Yeah. Somehow I care about things up to finite index, so I ignore the rotational part anyways. And they have to be torsion valued by they have to be torsion valued. I know for higher rank lattices they have to be torsion valued. So sorry. Okay.